Alright, let's rock. Tensor calculus. Okay, so we're going to skip through some of it, but...
What's going on, smart people? Bringing you the final episode of Tensor Calculus for Physics based on the book Tensor Calculus for Physics. I will leave a link in the description. I put quotations on final because I love Tensor Calculus. I'm going to make more videos on it in the future, but this is a nice spot to wrap things up with. The goal of this video is to arrive at Einstein's field equations. It's not going to be a formal derivation per se, but we are going to be able to make a series of arguments and arrive at it.
I look at this like
I
it's
think
crypto.
It'll be pretty satisfying.
And
maybe in a future
you
video
have to be able
I'll do
to
it
go
more
backtrack
formally
his
by
theory
varying the
thesis of a
Einstein-Hilbert action or
matrix
something like that.
that he's setting to a
in
very
a previous
specific
video,
prime
I think I was a little
model.
bit overly optimistic, thinking I could cover both Einstein's field equations and have a discussion on the interpretations of the different curvature tensors all in one video.
About chasing
I'm going to save that
derivatives.
curvature tensor stuff for a one-off video. I have made a video on the Riemann curvature tensor.
We're going to do that here
but
in a minute.
Not really assigning interpretations to what they mean, what the Riemann curvature tensor means, what the Ricci tensor means, and the Ricci scalar.
I knew
which
those
of these three
events,
different curvatures really mean.
I don't...
So I'm going to save that for like a one-off video in the future. But yeah, today is all on Einstein's field equations. If you'd like to catch up on some of the important videos that have led us to this, to be able to tackle it in a kind of simple manner, I'll leave links in the description, namely to the ones where I describe the Riemann curvature tensor and the Bianchi identities, and also how we can relate the metric tensor to the gravitational potential in the Newtonian limit. That's the stuff we're going to be pulling from for this video to make it go a little bit faster. Okay. Now, in one of those videos, we showed that in this Newtonian limit, we had that the we changed this color. We had that the Laplacian of the metric tensor in the Newtonian limit was equal to 8 pi g times mass density.
So,
and
Laplacians that are squared in
relativistic generalization of this mass energy density is all encoded in the energy momentum tensor.
Codes down
so that
into
is defined. So this
human
could
language and
be also
mathematical
expressed
functions.
in like a pseudo tensor form, as I should call it pseudo tensor because that's actually a thing. In this almost tensor form, as 8 pi g.
You're going to break this down.
T00
be built,
Newtonian
work
limit,
backwards.
T is the energy momentum tensor.
So again, you
and
already know your
80
80 day. You already know your 90-day model.
Just so I'm not tracing
and you're
down
starting your 90-day write out now. Take 90 days
now, if you're
to figure
unfamiliar
out
with the energy momentum tensor,
all
it
this
encodes
matrix
all the information of, you guessed it, energy, momentum, pressure, grad school, which is shear stress, all of that stuff is in here. So the 0,0 component is effectively the Hamiltonian density, it's like the energy density.
So
we also have the
one particle differentials of
which is the
turbulent
momentum
flow
density.
at the end of the barrel, man. And you could say that's anybody's thesis you want. You could say from the field equation here, just in
we can take the diagonal I terms, so Tii, which is the pressure. I know I'm using P for both, but we're not going to be actually using the energy momentum tensor, so just bear with me on that. And then also we have the off-diagonal components, I not equal to J, which is the shear stress.
I could take the next 8 years giving you a PhD in physics, or you could think about what this will do if you N1 half. Something like this, very usefully all the time. Now, the geometry of this equation, tensor vector to any other matrix of standard models in sectors, XY,
like a second-rank tensor equation. So the goal is to generalize Poisson's equation,
couple
to be
guys'
fully
timelines
relativistic.
just with my
and
next
the way that we're
guy,
going to start that off is by guessing that that generalization is going to be a
run.
second-rank tensor equation.
Field theory, hyperloop, particles, higher elements to lower elements, weights on the periodic table, give it a field in which weight by those numbers give me a way to identify its separation in a secondary
is now the full,
function.
It's not Newtonian limit, it's the full energy momentum tensor.
Hubble
and G
45
is to be determined.
Vector positions. And
I
these
think
Hubble
the
give
Bianchi
vector
identity
positions.
video it did, we actually did define what G mu is. We're going to pretend that we
gonna
don't already know. We're going to figure out what it needs to be. Okay.
What it needs to be is you in the stall mill right now. Everywhere you have a problem with heat, light, and sound right now. You don't understand what these things are. When you don't understand that, you don't know what it takes to make the field theory.
The criteria to narrow down what G
you got to quantify those by names, not just what it is, when it is, the number that it is for it.
Criteria.
And in there, you're going to start to get a chess game build on math theses, start back over into a really heavy...
What does the stuff need to satisfy? Well, first and foremost, as you can tell, it's a second-rank tensor equation, and I'm going to put a little asterisk there because...
But I want to get right to the saw program.
It's easy to see... I shouldn't say it's easy to see from
a tensor vector.
What it needs to reduce to, we can identify with something like a second-rank tensor equation.
Like,
but maybe that's just a simplification. Maybe that's a special case or something.
I need
but I'll
some
talk
kind
about
of
that
special way to
more in just a few minutes.
quantify the values in weeks, daily, weekly, monthly sets, and so I can begin to vector that position from the starting position.
So it needs to be,
for all the loading positions. They start to quadrant into massive singularities. What is the job? And it all goes on a platform for points, which correlate to the terms of loading that block. Being able to send that down the pipes, understand the fields around it aren't a particle, it's a block, and it's in the saw sideways to those limitations.
The constant Minkowski metric plus a static
metrics.
Kind of like a perturbation.
Anything has it. They all have it. I could try that matrix against this saw right now, but I'm using Schrödinger for the most part.
Which
Schrödinger, Penrose, Karl, Sagan, universe low.
Simple case being 8pi here, because
this from a top point of view to a flat panel against where those each individual systems have a definition and a name. Now we already know it's the operation. First, I got to teach you the operation and see how it works. And then there's a negative value, positive value, a standard value at a neutrino level for cut coefficients.
So that's a property we would like our field equations to inherit as well.
Moves on the saw face, turning over, and like I said, this is a tachyon base. Like I said, teach me certain cuts where the lasers are, what 3D dimensions there are to these kind of equations in one stacking field. This in this case is programming a saw. You'll get into A, B, C.
G alpha beta
code cipher for that XYZ matrix that scatters out to an infinity
beta
before he's putting in causal sets. He didn't want to chase them down, so
now this is a second-rank tensor equation,
like I
so
said,
these combinations we'd have to form
what could we say?
So
well, if the goal is to build field theory, I call
it
one
have to add
with a
certain
telescope
to make sure the end result is in fact a tensor. Because if you just take derivatives, we know that the derivative of a tensor in general is not going to be a tensor.
And therefore the observation of how fast can you find Mercury right now.
So we have these linear and second derivatives of the metric.
What orbital
we
is
also want to keep it
the
simple.
moon on right now?
Keep it
Sagittarius
simple,
or something,
some any more complicated than
point,
it needs to be. If nature presents itself in a more complicated manner, then yeah, we could add more corrections to it. In fact,
they are a specialized
that's
case.
People's careers, is trying to modify Einstein's field equations for higher order contractions of the Riemann tensor and its covariant derivatives and the Weil tensor.
Right now.
But for this, we're just not going to include it. If you think of all of that higher order stuff as being multiplied by a number, we're just going to assume that number's either really, really small or zero for this video.
This is really important.
I'm not an expert on GR though, so I don't want to ruffle any feathers for the people
on the Delaware River for location.
I don't know what I'm talking about.
Adjust that matrix.
How do we introduce these higher order terms? That's not this video. Okay, so we want to keep it simple. What else do we need? We also would like it needs to satisfy some form of local energy momentum conservation, right? So local EMT conservation. EMT is the energy momentum tensor. Mathematically, this can be phrased in terms of the energy momentum tensor being divergenceless. The fact that this is local, you should be a little bit more careful with conservation laws and divergence lists and making the connection between the two. But
military bases, technical colleges, and community colleges.
The reason I say conservation leads to divergence lists is because say that we were taking the divergence of the energy momentum tensor.
The names of these stone mills, given
that would be equal
Princeton,
to
T0,
T0, and let's set mu equal to 0 as well, plus DI. TI 0
D derivative, they all X.
Well, the 0 component of the energy momentum tensor is like the energy density, and the 0 derivative is something like a time derivative. So we get like a
metrics here.
dt of
this
an energy.
School, you said? So again,
and the I0 term,
how did this turn into
the momentum density?
The universe into grad school?
And we get the minus sign from the metric. Forget about that.
And it's going to lens that crap all to
gain some
happy hell.
And
then it has a lot to do with astrophysics.
So it's
pay attention to some stuff. Well,
like
time on top of the Himalaya, time under the bottom of the Mariancia. You hold the styrofoam ball, you did both.
So it's a statement of conservation of energy and momentum, or if we took nu equal to other things, so we have 4 continuity equations. That's all that I'm saying with local energy momentum tensor conservation. But if we're assuming left-hand side equals right-hand side, that means that G mu nu also needs to be divergenceless. So the divergence of G mu nu has to equal 0 as well.
It'll also mean gustance.
And
on their
oftentimes,
daily morning
the metric
rotation
tensor is a
of the
symmetric
maintenance
tensor.
serviceability. On minimum effort,
So
I know
that means
exactly
that
where
you
it
have
is, I know
10
where maximum
independent
effort is, I know
components.
exactly everything.
But this requirement here actually helps us reduce it to 6.
Like you said, veneer rocks
because
out
if
of
you
a
think
pile,
about
or
it,
just
we
a big
have
ass pile of
a
those you picked out. I had to pull out why one rock that weighs 100 pounds is worth shit, nothing, throw it to garbage, and this other one that weighs 100 pounds is a $20, $30 rock, you know, like whatever.
Gi nu. We're saying this tensor here is going to be in terms of second derivatives of the metric. Okay? Here we have
Give me another guy.
A spatial derivative of G, which means the right-hand side, the spatial derivative is not a time derivative.
It's a very good laced program.
Is a second derivative
if you're
of the metric.
hanging with him, you could probably
and here we're
pick
taking
up a
a time
few
derivative of G0 nu. But if this is supposed to be a
it's
second
a good
derivative
name.
of the metric,
Usually
that
when
means
you
that
catch somebody
G0
with
nu must only be a
Moore's
first
law,
derivative instead of a second
Jim
derivative.
coming
In other
around
words,
there with
we
Gresham's
don't
law.
get any dynamics
And
of
so
the
we
metric from these equations. They're more so
You
constraints.
couldn't handle
on the
this
coordinates.
inside here. There was something
So
that
there's
is
4
common
equations there,
practice
which is
on
why
that.
a lot of times you'll
You
hear
gotta know
that
the computer,
really there's 6
books,
independent
certain things on common cabinets,
components of the metric
ETF
tensor,
here,
if you think
EF,
about it this way.
NTF, whatever.
That's right. And then the final criteria is it needs to reduce to Poisson's equation, right? It needs to reduce
because somebody was smashing in the face. Oh, I
del
totally
squared phi equals 4
Catch you on the next one.
pi G rho.